So we are still in Unit 5, just at the beginning of it, sort of. And we are doing Target 5.4, which is actually Section 5.5 in your textbook. So even though it's Target 5.4, it actually goes with the lesson 5.5 in your book. So we're going to be doing bases other than E. And then, of course, all the applications that go with that as far as tangent lines and slope and all that. So I will differentiate and integrate functions in bases other than E. So here's what I'm talking about. We've been dealing with natural log, and we've been dealing with e to the x up to this point, and finding derivatives of both of those. So we've done those as our targets 1 and 2. So we're going to do bases that are not e. So instead of doing e to the x, we're going to do things like 3 to the x or 7 to the x. So instead of having base e, our base is going to be some other number. But remember, e is just a number, 2.718. So it still is a number, but it's a special number. And so we're going to be doing other values besides e as our base. And then over here, for the natural log, we're going to be doing other logs besides natural log. So we're going to be doing log base 3 of something, of x squared or whatever. All right, so we're going to be doing other logs. So when it says ln, that's natural log. But if it's another base, you have to write out the abbreviation log for log, and that has to have a subscript to tell you what base you're in, unless you're in base 10. If you're in base 10, then there's no subscript. So log by itself is base 10, ln is base e. If you're any other base, it's going to be log for logarithm, and it'll tell you what base you're in. So we're going to be doing bases that are not e. So we've already spent our time doing natural log, we've already spent our time doing e to the x. So now we're venturing into these other areas, these other logs and other bases. Okay? So let's talk about bases other than e, just reviewing what logarithms really are. So remember, a log with the little subscript is what base you're in. You're finding the log of y in base a, and the answer is x. And remember, the answer is always an exponent, because remember, logarithms are exponents. So to convert this into an exponential function, you take the base, raise it to your exponent, and it equals the argument here. So it's the log of the argument in this base. So this base a raised to the answer, which is the exponent x, will equal y. And that's what I have right here. A to the x equals y. So your base raised to your answer equals this expression that's behind the log. So taking this right here, what is the log of 8 in base 2? Well, the answer is 3, because 2 raised to the 3rd power equals 8. All right? Log of 625 in base 5, the answer is 4, because 5 raised to the 4th power equals 625. Okay? So I'm just converting them over here. So 5 raised to the 4th power equals 625. So you get this exponential function. Same thing, you can do fractions and things. So this is the log of 3 in base 9. The answer is a half, because 9, if you raise 9 to the 1/2 power, 9 to the 1/2, which means square root, you're going to get the answer 3. So 9 to the 1/2 equals 3. So this is converting between logarithm to your exponentials in our other bases that are not e. Okay? And again, like I said a few seconds ago, if it does not have a subscript, we are in base 10. It's called the common logarithm. So this would be base 10 here. So 10 raised to the 5th power would equal 100,000. And of course it does. 10 to the 5th power is 100,000. So just remember, that's the way you translate from a logarithm into an exponential. All right. So what we need to learn how to do is differentiate and integrate. So what's very helpful for us to be able to differentiate is to do the change of base formula. And this is how I do them every single time. If I'm trying to take the derivative of something that is based in a log in a different base, log base a of x, I always change it into natural log. I just always do. I do the change of base formula and I change it in a natural log. You can change to base 10. Okay, change into base 10 just means you take the log of the argument and divide by the log of A. So now these are both base 10, but I always do natural log. It's the natural log of the argument first, divided by the natural log of the base. All right, so down here as an example, the log of 8 in base 2, I would rewrite that as the natural log of 8 divided by the natural log of 2. So it's always the natural log of the argument divided by the natural log of the base. And we know this answer is 3 because 2 cubed is 8. And so this is also 3. So if you were to take this on a calculator and do the natural log of 8 divided by the natural log of 2, you would still get the answer 3. So it's still the same value. We're just changing what it looks like. And this change of base formula, like I say, is how I like to do derivatives. So I don't have to learn a new rule. And here I'll show you. All right, the first ones we have to learn. Okay, this is taking derivatives. So taking the derivatives of exponentials, and then down here taking derivatives of logs that are not base e. So let's talk about the derivative of an exponential that is not base e. Okay, so we're doing the derivative of a to the x. Well, just like e to the x, the derivative of a to the x is his own derivative. So the derivative of a to the x is a to the x, but we have to multiply by the natural log of a. Now, of course, this rule could have been written about e as well. If we did e to the x, it still could have been the same thing. I'll even put the little brackets to make it look the same. All right, the derivative of e to the x, well, the derivative of e to the x is e to the x, and we still could have multiplied it by the natural log of the base, which was e. But this would get redundant, would get really boring and tiring because the natural log of e equals 1. So this part's not necessary. So that's why the derivative of e to the x is just e to the x and not times natural log of e, because that equals 1. That's not necessary. But if you change the base and you do the derivative of a to the x, its derivative is a to the x times the natural log of a, and this value is not going to be 1. All right, so as an example, real quick here, if I was doing the derivative of 5 to the x, my answer would be 5 to the x natural log of 5. Okay, that would be the answer. So that's as simple as it gets. It's the derivative of anything exponential, just like e to the x is its own derivative. Okay, but you got to chain on the natural log of the base. It's just when we had e, the natural log of e, this would equal 1, so that wasn't necessary. So now when we don't have base e, we have to chain on that natural log of whatever the base number is. So that's how you do exponentials that are not e. Now over here, this is just talking about what do you do if your exponent is more than just an x. Well, we're going to do the same thing we did as we did with e. If your exponent is more complicated than just x, you've got to chain on the derivative of your exponent. So for instance, same thing. Let's say I had 5 to the x squared, and I was taking its derivative. Well, that's going to be 5 to the x squared. But then I have to chain on the derivative of my exponent, so I have to chain on 2x. And then I also have to chain on the natural log of 5, because that's my base. So we're still going to treat it like we did e to the x. You just have to remember to do that extra step of chaining on the natural log of the base. So this was still what you see, multiplied by the derivative of the exponent, and then remembering we got to chain on the derivative of the natural log of the base. Okay, so that's the one little extra step. Now, these last two rules down here, I never memorized these. Okay, I'm just going to tell you. The derivatives of logs that are in other bases, I never memorized them. I never do. Okay, because I use the change of base formula. Okay, so d dx, I'm going to change this and do the change of base formula using natural log because I already know how to take the derivative of natural log. So why would I learn a new rule about logarithms with other bases if I can convert it to natural log and I already know how to take the derivative of natural log? Why learn a new rule? So that's what I do every time. And it ends up being the same answer. I'll show you. So converting this log of x in base a, remember to convert this using the change of base formula. It's the natural log of the argument divided by the natural log of the base. Okay, so natural log of x divided by natural log of a. Now what I want to do is take the derivative of this. Okay, now natural log of a is just a number, so that's a coefficient. So that's not going to go anywhere. 1 over the natural log of a, because natural log of a is just a numerical value. So what I'm really taking the derivative of is natural log of x. We know how to do that. The natural log of x, its derivative is the derivative of this function divided by the function. So that's going to be 1 over x. Notice this is the same answer as up here. So you get the same answer, but it's so much easier than trying to memorize a new rule. Same thing over here. The only difference is this x is not an x, it's going to be a function. So we have to remember to chain on the derivative of this function. It's going to be in here like we've learned it. Okay. So I'll go ahead and just do one to show you. Okay, the derivative, let's say I was doing log base 2 of x squared. Okay, and that's not just an x, where over here it was just an x. So I'm going to say it's log base 2 of x squared. So I would first change it into a change of base formula situation. So I'm going to do the natural log of x squared divided by the natural log of 2. Okay, so over here I could have given that a number if I wanted to. Say I put a 2 there, this would have been natural log of x over natural log of 2. So this is 1 over natural log of 2, which is just a number. Okay, so again, taking the derivative of this, the 1 over the natural log of 2, that's just a number down there. So really all I got to take the derivative of is this natural log, which we already know how to do. It's the derivative of that divided by that function. So here is that rule. So here's the derivative that I do on the top up here, and then the u is my function. So it's derivative over function, and then you've got this 1 over ln of a, which is right here, 1 over ln of 2. So I do the change of base formula first, and then just use my natural log rules, which we already know. No need to learn a new rule. It's really the same, okay? But if you want to memorize these, you can. But I think it's easier just to go ahead and convert the problem you're doing into a natural log problem using the change of base formula, and then just use your natural log rules. All right? Now, integrating, we are going to learn how to integrate a to the x. Well, its derivative is a to the x times ln of a. So the antiderivative is a to the x divided by ln of a. So when you do the antiderivative, you divide by the natural log of a. So that is really pretty easy. Taking its derivative, remember over here, taking the derivative, you multiply by ln of a. So to integrate, you're going to divide by ln of a. So the antiderivative of a to the x is its own antiderivative, and you divide by the natural log of the base. So if I had the problem, I was integrating 7 to the x dx, that would be 7 to the x, he'd be his own antiderivative. Then I have to divide by the natural log of my base 7, and then add c. That's the answer. So notice if this was e to the x, you would be dividing by natural log e, which is a 1. And so that's why we didn't study it that way with e, because natural log of e is 1, and that would get really redundant and old to keep doing, dividing by natural log of e when it's not necessary. All right. So on this video, I'm going to go ahead and do the derivative problems, and then I'll make a separate video for the integration problems, okay, that are somewhat a little bit more involved. All right, so find the derivative. So here, y prime, this is doing 2 to the x, so the derivative of 2 to the x is its own derivative, and then I just have to chain on the natural log of the base 2. That's it. That's all there is. And then over here, y prime, he's his own derivative, 2 to the 3x. I have to remember to chain on the derivative of my exponent, which is 3. I also have to remember to chain on the natural log of the base I'm in, and that's your derivative. That's all you do. You don't have to multiply anything out, don't have to do anything else. That's how you take the derivative of bases that are not e. So this example number 2 is the ones where we're taking the derivatives of logs. All right, so like I said earlier, I changed these to natural log. So I would do natural log of cosine divided by the natural log of the base right here, which is base 10. Okay, which those didn't really have to be written there since that's the common log, but they just wrote them there. All right, so I would first change both of these using the change of base formula. So this would be natural log of 2x divided by the natural log of what base we're in, which is 10. Okay? So now, to take the derivative, y prime. This natural log of 10, that's just a number. So I'm going to keep 1 over the natural log of 10 as my coefficient. And all I got to do is take the derivative of this numerator part right here, which that's a ln problem. So when you take the derivative of ln, it's the derivative of this function, which would be negative sine, divided by that function, which is cosine. And then I could abbreviate that if I wanted to. I could make it negative tangent. So negative tan divided by the natural log of 10, because sine over cosine is tangent. So this would be negative tangent divided by natural log of 10. So you could clean it up just a little bit. And remember, this is multiplication, not subtraction. All right, over here, taking my derivative. Again, this natural log of 10 in the bottom, that is a number, so that's a coefficient. So I have 1 over the natural log of 10, so that's just my coefficient that I'm going to keep when I'm taking my derivative. And all I need to do is take the derivative of ln of 2x. And we know how to take the derivative of natural log. It's the derivative of the function, which is going to be 2, divided by the function, which is 2x. And this is multiplication. I could clean this up by canceling the 2's. So my answer would be 1 over the natural log of 10 times x. You could put the x in front so it doesn't look like natural log of the quantity 10x. It doesn't have parentheses anyway, so it shouldn't be read that way. All right, so anytime you take the derivative of a log that is not base e, so it's not natural log, I always rewrite it using a change of base formula, and I always rewrite it as natural log. So then my denominator is always a coefficient. Okay, so I always have 1 over my denominator. These are always going to be numbers. So then you're only taking the derivative of the natural log of the numerator. So that should be where your variable is. All right, and we know how to take the derivative of natural log. It's the derivative of the function divided by the function. So that's f prime divided by f. We already know how to take the derivative of natural log. The ln goes away, and it's just the derivative of the argument behind it divided by the argument, which is the function behind it. That's what it's called. All right, so we know how to do that already. So we might as well apply something we already know so that we're not learning a new rule, okay? The less rules we have crammed up in our brains, the better off that we will be learning the ones we need to know, right? Okay, so the rest of the next problem is all integration. So I'm going to make a new video for integration so that you don't have one long video.